point is just to say that this whole discussion becomes confusing because Smith and every other organic chemistry book that I can recall has treated what are really kind of a bad design with equal attention to the good design, and they don't point out the difference. It turns out that there is also a different reaction mechanism where there's only one chemical species in the rate determining step, a nucleophilic substitution that's only got one chemical species in the rate determining step, and there is also an elimination reaction where there's only one chemical species in the elimination step, the rate determining step. So it's a unimolecular, it's an E1 reaction. Now, both of these, well, they've got great similarity. If we start with, once again, the same molecule, but if in this case, let's say in the absence of a strong nucleophile or a strong base, that on its own, and in no great hurry, but on its own, that alkyl halide might ionize. So if it ionizes, a bromide, if this happens, if the bromine nucleus and the pair of electrons that had bound it to the organic framework, if they both leave, on their own, we say that the alkyl halide has ionized. It's broken apart into a cation and an anion. Now, if that is the case, suddenly this organic molecule, which now has a positive charge, it's a so-called carbocation, it's totally active and it's going to do something quickly. And the problem is it can do a number of things. It's very reactive. If it encounters even a bad nucleophile, let's say I'll write in weak nucleophile. Here's an example of a weak nucleophile. Water. The oxygen has two unshared pairs of electrons, so if that water bumps into that very reactive carbocation, this could happen. The water would bang up against it, and add to it. Now, I look at that and I think it would be useful for you to look at that and say, that's actually just an alcohol molecule that's got an extra proton. So if it loses its proton and the charge, the result is that the alkyl bromide, which became a carbocation, became an alcohol. Now there's another important thing, which you might remember from discussions last week, which says that the carbocation actually has this other power. It can rearrange from a secondary carbocation. This is a secondary carbocation because the positive charge is on a secondary carbon, a carbon which itself is bonded to two R groups. But if the hydride that's on carbon 3 in this molecule just wanders down, then we have a rearranged carbocation, and now what had been a secondary carbocation becomes a tertiary carbocation. We describe that as a hydride shift. H with two electrons is a hydride, and it shifted from that carbon down to that carbon. Again, we don't show it because we don't have the habit of drawing in hydrogens because they make us crazy. Now, there is another possibility of what might happen to this. And that is that even a weak base will come along and steal a proton. So, for example, we may get that alkene, or from this carbocation, we may get that alkene, where a base has stolen a proton from a beta carbon. There's one other thing which I haven't shown, is that this tertiary carbocation, that could receive a water molecule and then be deprotonated and become an alcohol. So all of those arrows and all of those possibilities are the reason I view these unimolecular reactions as only havoc, and that I don't encourage you to think of those as reasonable good strategies. There are things that will happen that will just make us crazy. So now, in just one more whiteboard of information, I want to summarize, and I hope it starts to get simple, it appears simple to you. If we have an alkyl halide, and we have a nucleophile, what we define as a strong nucleophile, usually that's understood if the chemical species has a pair of electrons that it can use to form a bond to a carbon, and it often is signaled to be strong by having a negative charge. Or if we have an alkyl halide, it can be the same alkyl halide in the presence of a strong base. Again, the strong base, by definition of a base, it's got a chemical species with a pair of electrons that it can use to yank a proton off a carbon molecule. And it's a code saying this is a strong base because it has a negative charge. Now, in these, we have pretty well-defined reactions. A strong nucleophile attacks the alkyl halide and produces a product, substitutes the nucleophile for that halide and displaces the halide. In the reaction of a strong base with an alkyl halide, we introduce this new language, which is useful. We say, in this case, a halogenated carbon will be the alpha carbon, and any carbon bonded to the alpha carbon will be a beta carbon. Now, in the reaction of a strong base with an alkyl halide, the thing that the base will do will be to grab a proton from one of the beta carbons. So I'm not going to draw, well, I'll draw a curve now. If the base grabs a proton from that beta carbon and frees a pair of electrons here to form a pi bond and displaces a bromide, if those three curved arrows happen, the product would be this alkene. Now, if on the other hand, the base abstracted a proton from the other beta carbon, in that case, the product would be, I'll put down here, the black product. That alkene, you'd get still a mixture there. We define one as a terminal and the other as an internal alkene. Now there's one more thing. The unimolecular reactions, which would be the SN1 and the E1 reactions, these are so unpredictable that they're really kind of useless for a synthetic strategy. They might only happen kind of by accident. But if on its own, an alkyl halide were to ionize, if it were to spontaneously lose a bromide, it would produce a carbocation. Now, you will understand now that a hydride shift will probably happen much quicker than any other thing, so that secondary carbocation becomes a tertiary carbocation. And then, in the presence of any chemical species which can act as a base, that is a proton grabber, it could produce a mixture of alkenes, and it might produce this one. There are two different beta carbons. And the possibility also is that a nucleophile might succeed in forming a bond even to that tertiary carbon. So we could say another possibility in the presence of a nucleophile is and since so many different products are possible, it's simply not a good strategy. We'll focus on the bimolecular reactions because they're useful. It's easy.